Hey everyone, and welcome. Today, we're going to put on our detective hats and solve a really cool chemical mystery. We're going to take a substance that looks simple, but using the power of chemistry, we're going to figure out exactly what's hiding inside. So let's dive right in. So picture this. Someone hands you a test tube filled with this white crystalline powder. It looks like just one pure thing, right? But is it? How in the world can you figure out its true composition without just, staring at it? Well, that is the exact puzzle we're going to solve together today. And here's the first secret of our mystery. That powder isn't one substance at all. It's actually two. It's a mix of sodium chloride, yep, that's just regular table salt, and another compound called potassium chlorate. The tricky part? They look identical. You could stare at them all day and you'd never know it's a mix. Our mission is to find out the exact percentage of each one in our sample. Now, to solve any good mystery, you need that one critical clue, right? The one piece of evidence that cracks the whole thing wide open. And in chemistry, that clue, it almost always comes from a chemical reaction. Here it is. This is our key. When we heat our mixture, only the potassium chlorate, the KClO₃, does something interesting. It decomposes. It breaks down into a different solid, potassium chloride. And, here's the most important part, it releases oxygen. And see that little G there for gas? That is the hero of our story. And here's the other half of our clue. The sodium chloride, our friendly table salt, is totally bored by the heat. It doesn't react, it doesn't change. It just hangs out in the test tube while the potassium chlorate is having this big reaction. And this is crucial. Only one part of our mixture actually changes. And this right here, this is the foundation for our entire investigation. Think about it. Since the only thing that actually leaves the test tube is the oxygen gas floating away, any mass that we lose, it has to be the mass of that oxygen. It's a direct measurement. Okay, so we've got our main clue. We know what we're looking for. Time to head to the lab and actually gather the evidence, just like a real detective. The process is super methodical, like a detective following a checklist. First, we get a super precise starting weight for our mystery powder. Then, we bring in the heat with a Bunsen burner. This is what kicks off the reaction and makes all that oxygen gas bubbled away. After it's all done, we have to let it cool down completely. That's important for an accurate measurement. And then we take our final weight. That difference between the start and the finish, that's our smoking gun. Yep, that little bit of mass that just seemed to disappear, that's not magic. That is our key piece of evidence. It's the exact, measurable weight of the oxygen that was released from the potassium chlorate. All right, now for the really fun part. We have our evidence, we know the mass of the oxygen that escaped. Now it's time to pull out our chemical decoder ring and figure out what it all means. And that decoder ring, it has a fancy name, stoichiometry. Now, I know it sounds super complicated, but don't let the word intimidate you. Seriously, all it is a recipe. It's the recipe for a chemical reaction that tells you the exact proportions of everything involved. See, our reaction recipe, that balanced equation we looked at, tells us something incredibly specific. It says that for every 3 parts of oxygen gas we create, they had to come from exactly 2 parts of potassium chlorate. It's a fixed ratio. It never changes. So if we know how much oxygen left, we can do some simple math to figure out precisely how much potassium chlorate we must have started with. So here's how the logic flows. It's actually pretty beautiful. We take the mass of the oxygen we lost. That's our measurement. Then we use our chemical recipe, our stoichiometry, to work backward and finds the mass of the potassium chlorate that made it. And finally, we just compare that to the total starting weight of the whole mixture. And boom, we get our percentage. And there it is. Case closed. By following the evidence and using our chemical recipe, we've totally uncovered the true identity of our mystery powder. We can now say with 100% certainty what percentage was potassium chlorate and what percentage was just plain old table salt. So we solved our lab puzzle, which is awesome, but you might be asking yourself, okay, but why does this actually matter in the real world? Well, it turns out that this idea of following a chemical recipe is one of the most fundamental and important tools in all of modern science.
Seriously, stoichiometry is everywhere. It's how pharmaceutical companies make sure the dose of medicine in a pill is exactly right. Not too much, not too little. It's how manufacturers calculate precisely how much raw material they need, which saves a ton of money and prevents waste. It's used in food science. It's used to measure pollutants in the air we breathe and the water we drink. It's a tool for precision and safety in basically every industry you can think of.
So, the next time you see some simple substance, maybe even the salt on your table, remember our little white powder. Remember that chemistry gives us the tools to look so much deeper, to measure what we can't see, and to solve the amazing mysteries that are all around us every single day. It just makes you wonder, doesn't it? What other secrets are out there, hiding in plain sight, just waiting for a curious mind to find the right chemical key to unlock them?